All right, let's talk about Java Maps. We all use them, right? They are the absolute workhorses for managing data. But have you ever really stopped to think about how they actually work? You know, how they pull off that lightning-fast performance we take for granted? Well, today we're pulling back the curtain. We're going deep inside the engine of Java's map implementations, and we're going to start with the one big problem they were all built to solve.
So let's start with a really practical problem. Picture this. You've built a system, and it's a huge success. You have 1 billion users. Now, when one of those users tries to log in, you can't afford to scan through 1 billion records one by one to find their profile. That would take forever. You need to find them almost instantly. This exact challenge is why hash maps were invented.
So what are our options here? Well, we could just dump all the users into an array and do a linear search. But as you can see, that's an O of n operation. The more users you add, the slower it gets. It just doesn't scale. Or we could use the, let's call it magic, of a hash map. It gives us an average lookup time of O of 1. That's constant time. It literally doesn't matter if you have 10 users or 1 billion. The speed is basically the same. It just jumps straight to the right spot. But how?
Well, that magic has a name. It's called hashing. And this isn't a data structure itself, it's the core technique, the engine that powers the whole system. So let's peel back this first layer and see what's really going on.
Hashing is, at its heart, a pretty simple process. You take a key, it could be anything like a username string, and you run it through a special function. This function then spits out a number, a hash code. Now here's the crucial part. That hash code tells us the exact address, the exact array index, where we're going to store and later find the value associated with that key. Now what's really fascinating is how Java's hash map specifically does this. It's like a little 3-step dance. First, it calls the key's built-in hashcode method to get an initial number. But, and this is clever, it doesn't just trust that number to be perfect. So in step 2, it does this bit mixing operation. It's basically scrambling the bits of the original hash code to spread them out more evenly. This is super important for preventing different keys from all clumping up in the same few spots. And finally, to get the actual array index, it uses a super fast bitwise AND operation. It's way faster than using something like the modulo operator.
Here's a great way to think about it. Imagine a huge library. You don't walk down every aisle reading every single book spine to find the one you want, right? No, you look up its call number in the card catalog, and that number tells you exactly which shelf to go to. A hash function does the exact same thing for your data.
Okay, so that all sounds great, but what happens when the system isn't perfect? What if, somehow, 2 completely different books were assigned the exact same call number? This brings us to our next big challenge, the collision problem. This is the million-dollar question. I mean, the whole goal of a hash function is to give a unique number for every key. But with a limited number of possible indexes, it's pretty much inevitable that eventually 2 totally different keys are going to produce the same index. So what do? We call this event a collision. Let's imagine we have 2 users, one named Jeff and another named Bob. It's totally possible that after Java does its whole hashing and bit mixing dance, both of their usernames map to, say, bucket index 123. Now, if we just put Bob's data there, we overwrite Jeff's profile, and he's gone forever. That's obviously not going to work. So what Java does is actually really simple and elegant. It uses a strategy called chaining. When that collision happens, it doesn't overwrite anything. Instead, it starts a linked list, right there inside that one bucket. The first entry points to the second to the third, and so on. So when you need to get a value back, Java first hashes the key to find the right bucket, and then it just walks down that short list, using the good old equals method to find the exact key you were looking for. Chaining is a fantastic solution, but it's not foolproof. It has a potential weakness. What if you have a really bad hash function, or you're just incredibly unlucky, and one bucket ends up with a super long linked list? Well, searching that list is, you guessed it, a linear search. Our performance suddenly degrades right back to O of n, and the entire purpose of using a hash map is defeated. This very problem is where the engineers behind Java 8 introduced a truly brilliant optimization. They figured out a way to upgrade those overcrowded buckets right on the fly. The magic number is 8. This is a constant inside HashMap called the treify threshold. When the number of entries chained up in a single bucket grows to be more than 8, HashMap says, nope, this list is not efficient anymore, and it triggers a pretty radical transformation. It converts that slow, plodding, linear linked list into a highly efficient, self-balancing red-black tree. just like that. And this one change transforms the search inside that bucket from a slow crawl back into a lightning-fast binary search. It instantly drops the time complexity from O of n down to O of log n, which protects the entire map from those worst-case performance scenarios. It's an amazing safeguard.
Now, the really interesting part for us developers is the specific rules for this treeification. It's not as simple as just hitting 8. The list has to have more than 8 nodes, and the map's total capacity has to be at least 64. Why? Because if the map is still small, it's actually cheaper to just resize the whole table and spread the keys out. And get this, it even works in reverse. If you remove entries and the tree's size drops back down, it will convert back into a linked list to save memory. So cool.
So that's the deep magic humming away inside a hash map. But HashMap is just one member of a whole family of map implementations in Java, and each one is tailored for a specific job. Let's do a quick tour.
First up, we have the one we've been talking about, HashMap. It's the default choice for a reason. It's fast. But you have to remember its key characteristics. It makes absolutely no guarantees about the order of its elements. It is not safe to use across multiple threads without you adding synchronization yourself. And it has this little quirk where it allows one null key.
Now, what if you actually need a predictable order? Well, that's exactly what linked hash map is for. It's basically a hash map, but with an extra doubly linked list running through all of its entries. This lets it remember either the order in which you inserted items, or, and this is really powerful, the order in which they were last accessed. This is the secret sauce for building things like simple LRU, or at least recently used caches.
And what if you don't care about insertion order, but you absolutely need your keys to always be sorted? Then you need to reach for TreeMap. Now, TreeMap is different. It doesn't use hashing at all. Under the hood, it's one big red-black tree. This means all of its operations are O of log n, and it keeps the keys in sorted order all the time. This is your go-to when you need to do range queries, like find all users whose names start with the letter J.
Okay, finally, let's talk about building multi-threaded applications. The original legacy solution for this was Hashtable. It achieved thread safety by just slapping one giant lock on the entire map, so only one thread could touch it at a time. Simple, but terrible for performance. The modern and much better solution is Concurrent HashMap. It uses a really sophisticated technique of fine-grained locks on different sections of the map, which allows for incredibly high-performance reads and writes from many threads at once.
Phew! Okay, we have covered a lot of ground, from the nitty-gritty bit-level details of hashing all the way up to the high-level differences across the entire map family. So let's bring it all together into a clear, actionable guide you can use.
And here it is, the ultimate map cheat sheet. You can see the key trade-offs right away. For pure speed, HashMap and linked HashMap give you that O of 1 performance, but you give up thread safety. If you need sorted keys with TreeMap, you have to accept that slightly slower O of log n performance. This table lays it all out so you can make the right decision for your specific needs.
And to make it even simpler, here's the final advice boiled down. If you just need raw speed and you're in a single-threaded environment, HashMap is your best friend. If you need to iterate through your items in a predictable order, grab linked HashMap. If your keys must be sorted, TreeMap is the only real choice. And for any serious high concurrency application, you should absolutely be reaching for Concurrent HashMap.
So, here's the real takeaway from all this. Knowing these internals isn't just academic trivia. It actually makes you a better developer. It gives you the power to choose the right tool for the job every single time. So, I'll leave you with this question. Take a look back at your own code. Now that you know how all this works, which map have you been using without realizing there might have been a better, more performant, or more correct option?